Mostly because I just switch this a little bit. Mostly because we just don't have time to do everything in here, and it just kind of is what it is. So I kind of cut down a lot of the meat in this chapter to just focus on the parts of the chapter. So with that said, let's talk about the hormones that come out of our anterior pituitary. So our anterior pituitary is influenced by those inhibiting and releasing hormones that come out of that hypophyseal portal system, right? Telling the pituitary to either release or to stop releasing particular hormones. And I believe last class we drew like a kind of flow chart up here showing that cascade of events. It's not going to work. There we go. So looking at kind of a first level of control where our hypothalamus releases hormones. The second tier control is where our anterior pituitary releases hormones, which goes to a target organ. And then sometimes those target organs release a third level of hormones to go out into the circulation. So the anterior pituitary releases a couple hormones that affect other glands. Hormones that affect other glands. So, in other words, these are hormones that are going to go to other endocrine organs and tell them to release other hormones. So one of them is called thyroid stimulating hormone, or TSH. It does exactly what the name says. It stimulates the thyroid. It tells the thyroid when to secrete thyroid hormone. There's also adrenocorticotropic hormone. If you look at the word, it sounds complex. You hear that word adrenocorticotropic and you're like, what the what, right? Adreno makes you think of what? Adrenaline. Yeah, adrenaline or adrenal glands, right? Cortico is referring to the cortex. So the cortex of the adrenal glands, which we'll talk about when we talk about the adrenal glands, this is a hormone that stimulates the adrenal cortex. So it's going to stimulate the adrenal cortex to release hormones. So ACTH, and I'm just going to abbreviate up here for sake of time, but ACTH, stimulating that adrenal cortex. There's also prolactin. Prolactin is going to stimulate the mammary glands. So we mentioned last time the posterior pituitary secreting oxytocin. Oxytocin is milk ejection. Right, that's actually releasing the milk from the body, letting it come out. Prolactin is actually creating the milk. So it's kind of turning the mammary glands on and getting milk to actually be produced. So we have luteinizing hormone. LH, luteinizing hormone. This is going to work on the gonads. So by gonads, I mean ovaries and testes. And the gonads are obviously different in males and females. So LH, luteinizing hormone, has a different effect in males and females. In males, it's going to stimulate the production of testosterone. In females, it's going to stimulate the ovaries to release estrogen and progesterone. So both of these are, let me back up. The luteinizing hormone is released in response to gonadotropin releasing hormone. So gonadotropin releasing hormone comes down from the hypothalamus, GnRH, from the hypothalamus, and that stimulates luteinizing hormone to be released. So when luteinizing hormone is released, then that triggers either testosterone or estrogen or progesterone. So it'll look something like this: GnRH from the hypothalamus goes down, tells our anterior pituitary, right, that's through the portal system, tells our anterior pituitary to release luteinizing hormone, which goes down to the gonads, right, which in males will release testosterone, and in females, we're talking estrogen and progesterone. Right, so the stimulation of estrogen and progesterone, that's going to trigger ovulation in a female. Whereas what testosterone does is it triggers sperm development in males. So it's kind of the same thing, right? Egg development, which is what ovulation is, and sperm development is just developing, or the finalization of those gonads, finalization of the gametes, I should say. But that's all triggered by GnRH, which comes from the brain. Then we have FSH, which is another reproductive hormone. FSH is commonly confused with LH because it's working in that same region. It's still working on the gonads, but FSH is doing a totally different job. What FSH is doing is it's stimulating the testes to develop more sperm. So it's fueling sperm development, whereas in the females, it's releasing mature follicles. So it's still going to work on the gonads, but the roles are slightly different. FSH and LH together produce lots of testosterone and estrogen in the gonads. The follicle-stimulating hormone specifically in males is sperm development. LH is testosterone release. So they kind of go together, right? They kind of go together. Anterior pituitary, under the direction of GnRH, same idea, will release FSH. FSH goes to the gonads, and we have the same pattern here. In males, it's going to trigger testosterone, which triggers sperm development. Right? Here, this is more specifically the sperm development piece. So the testosterone is coming from the LH. The FSH is triggering the sperm development. So the two of them need to be present in order to have healthy motile sperm. And likewise in females, the estrogen and progesterone are released because of LH. But it's really the FSH that triggers this follicle, this egg cell, to be fully mature for release. So FSH here, mature egg cell. Right? But you need the estrogen and progesterone from LH in order to have that. Right? And this is why reproduction is super complicated, and we're just kind of sitting it on a shelf for right now, and you'll come back and revisit it next semester because we have a whole chapter worth of hormones to talk about, and there's a whole chapter dedicated to reproduction next semester, and it largely focuses on hormones because it's all regulated by hormones. Growth hormone. So this one is not necessarily affecting other glands. Growth hormone is going to go out and affect the rest of the body. So growth hormone is sometimes just abbreviated GH. Right? So growth hormone is going to affect our skeletal muscles, our bones. It affects metabolism. This is one of those kind of fire-burning engine type hormones. Growth hormone revs you up. When we think about growth hormone, you're probably already thinking about growing, right? But when you think about growing, you should think about activating the cells, actively dividing, metabolizing, using fat stores, using blood glucose, right? Making lots of energy. Because that's what growing is, right? You're making lots of energy and then you're using it to grow. So growth hormone is a metabolic hormone. It's one of those that can be abused. It's kind of sold on like the black market, so to speak, to people that want to lose weight quickly or bodybuilders that want to build muscle mass quickly. Growth hormone is one of those things that they can inject themselves with to kind of give them that extra boost in their metabolism. So short-term effects of growth hormone, right? Fat breakdown, glucogenesis in the liver, right? Breaking down glucose in the liver, again, metabolizing all of our kind of metabolic stores, right? All of our blood glucose, all of the fatty acids that are kind of sitting around are used to build new muscle or new structures in the body. So again, this is a strong anabolic hormone. It's a building hormone in our body. It's something that's going to trigger growth and development. Long term, again, this affects every cell in our body. It's going to decrease our blood glucose. It's going to pull glucose out of our blood, stick it in the cells so that it can be used, right? Growth hormone is going to play a huge role in adults promoting the building of muscle, right? So growth hormone is present in people who are physically fit, people who are actively using their bodies every day, and people that are staying, like I said, staying fit. And so that's why growth hormone is one of those kind of things that a lot of people try to get secretly and inject themselves with to lose weight or cut weight or whatever for like a competition or a show or a vacation maybe, I don't know. So this is just showing how it works, right? Short-term effects, mobilizing metabolic reserves. Long-term effects, growth, metabolism, muscle mass. So growth hormone is stimulated by growth hormone releasing hormone, so GHRH. GHRH, right? GHRH, releasing hormone, so that tells us that that's coming from the hypothalamus through the portal system to tell our anterior pituitary to release, right? And it gets inhibited by something called somatostatin, which is another, it's kind of an antagonist. Somatostatin gets released when your bones and muscles are growing too much, or when your bones and muscles are growing more than how you're using them. Remember that kind of hypertrophic effect when we talked about our skeletal muscle and muscular system. If you don't use it, you lose it. So somatostatin will be released from those cells if you're not using it. So our thyroid gland, so this is moving on from anterior pituitary. So all of these come from anterior pituitary. Prolactin, adrenocorticotropic hormone, LH, FSH, TSH, and growth hormone. And then we also had the two that are secreted from our posterior pituitary. So moving on into other endocrine glands, we have the thyroid and the parathyroid. So we're just going to kind of move down the body. Our pituitary, of course, in the brain. Our thyroid and parathyroid are in the throat, in the larynx region right here. You can actually kind of feel your thyroid if you put your hands right above that jugular notch and you swallow. When you swallow, your larynx elevates because it's closing the epiglottis to block the flow of saliva down into the respiratory passageway, but you can feel a little something come up from the bottom there. That's your thyroid gland that kind of like rides up a little bit as your epiglottis elevates and you swallow. And so it's kind of shaped like a little butterfly. That's the thyroid. The parathyroid glands are on the back of your thyroid gland, and they're actually small paired hormones. And so, I don't know why that's there. There we go. There we go. There it is. So it's kind of shaped right there, again, as we mentioned. It has a couple different regions to it. I'm going to erase this here so we can talk about the microscopic, since histology is important to us. So if we looked and we kind of zoomed into our thyroid, we would see lots of these bubbles called follicles. So each of these structures are called follicles. And they're surrounded by cells, epithelial cells. Right, epithelial cells cover and line, and so that's what these are doing. They're covering and lining these little areas here. I'm just drawing a bunch of cells. So the cells that surround the follicle are called follicular cells. So these follicular cells will secrete, these are the ones that secrete the thyroid hormone, T4 and T3, which we'll talk about in a minute. And then this area in here is called a colloid. You'll see it in lab when we do this for histology. It looks like a big bubble under there, and it's filled with, like, you know, that pinky purpley dye that is in all of our histology slides. But this colloid contains a high concentration of iodine atoms. So iodine is used to make our T3 and T4 thyroid hormones. Parafollicular cells are the cells that don't surround the follicle, that don't surround the colloid. So they would be like these guys here. And sometimes these are called C cells. They secrete calcitonin. we've talked about calcitonin before. It helps with blood calcium levels, right? It helps maintain blood calcium levels. There's what we just drew, right? The colloid is that empty space in the middle. It's where lots of iodide is dissolved. So the iodide that's in here comes from our diet. You get iodide, it's a mineral, it's in vegetables, it's in fish, right? So we use that from our diet, break it down, absorb it through our digestive tract, stick it here in our thyroid gland. So if you're not eating proper nutrition, guess what? You don't have enough iodine molecules. Guess what? You don't have enough thyroid hormone. Guess what? You're not going to be able to do the things that you need to do, right? Thyroid hormone is very similar in function to growth hormone. Growth hormone and thyroid hormone are our main engine lighters. They're the ones that are really fueling the fire in our body. And so without growth hormone and without thyroid hormone, you're going to be tired. You're going to have very thin hair and thin nails and dry skin. And you're going to be very lethargic. And your mind's not going to work properly because you just don't have the energy to think and the energy to put into the things that you have to do, right? And so it can really affect you physically, not just, with weight gain and that type of a thing. It can have really, really detrimental effects. So all of that iodine is stored here. Follicular cells surrounding that colloid make that, and they use it to, or they take the iodide, I should say, to make the T3 and T4 that we'll talk about. Here you see some of those parafollicular cells or C cells, that are not surrounding the colloid. So the parathyroid glands, these are small individual glands. They're kind of on the back of our thyroid. So people that have had, does anyone know anyone that has had a thyroidectomy, had their thyroid taken out? It's a pretty common procedure. Sometimes they have it taken out because it's not working properly. And when the thyroid doesn't work properly, it tends to swell. It gets really big, creates this condition called a goiter. And it's this very enlarged kind of bubble in your neck. It can be very uncomfortable. And obviously it's one of your first indicators that something's not working right in your thyroid. So typically what they'll do is they'll remove part of it or they'll take the whole thing out. But then the dangerous piece is you have another gland there on the back of your thyroid. You have your parathyroid gland there. And your parathyroid gland secretes parathyroid hormone. So that makes it easy, right? So thyroid gland secretes thyroid hormone. It also secretes calcitonin. Parathyroid gland secretes parathyroid hormone. It couldn't be any easier, right? Parathyroid hormone are going to work in balance with calcitonin for blood calcium levels, that blood calcium balance. So let's talk about T3 and T4. So they're named because of the number of iodide ions that they need. So T4 is going to use 4 iodide atoms. T3 is going to use 3 iodide atoms to make it. So T4 is actually converted into T3 in some tissues. Both of them are used widely throughout the body, but different tissues are going to prefer T3 to T4. So they both have the same general effects in your body. Regulating metabolic rate, thermoregulation. Again, this is why I think of like stoking the fire. Like, have you ever like made like a campfire or had a fire in like your fireplace at your house? And some of the things you have to do to get that fire going is you have to put fresh, dry wood in it, and you have to make sure there's proper oxygen flowing into there to really fuel the fire. And once those two things are there, your fire's going to grow. And that's exactly how thyroid hormone works. Think of thyroid hormone as that dry wood and oxygen going into your body to light the fire. It's literally going to fuel your body, give you lots of metabolic energy, make your cells really efficient at converting nutrients into ATP energy, at building proteins, building muscle, repairing structures, etc. So it's there to regulate all of that metabolism, and because body heat is a byproduct of metabolism, right? Our chemical reactions in our body are only 60% effective. The rest of it just losses heat. It's also by default producing the body heat for our body. So people that have had a thyroidectomy or people that have thyroid problems have chronic body heat temperature regulation issues. Maybe they're constantly cold. And I mean, I say that loosely because this is the time of year where I'm constantly cold, and a lot of people are constantly cold. I won't be warm until my heat is on in my car for 10 minutes blasting, and my seat heaters are on and all of that stuff, right? But that's not the same thing as someone that has a thyroid issue, right? It's people that have a thyroid issue, they get very hot and very cold very quickly because their body's not regulating it properly. And likewise, the opposite, having a hyperactive thyroid where you're producing too much, you're what I might call a sweaty person. You're someone who's constantly sweating. I took this class in undergrad. It was called mammalogy. It was a study of mammals. It was actually a really cool class. And because I've always loved animals. Anyways, the guy that I sat next to in lab, I have never met a sweatier person in my whole life. I think he took steroids or some drug to make him super sweaty. We're sitting in a basement lab, and he's dripping sweat. Not like physically dripping sweat, like onto our papers. Like, I'm sorry, I'm gonna scoot over here. So I don't know if he had a thyroid thing or a steroid thing or whatever was going on, but yeah, he probably had something going on with his thyroid, or maybe he was kind of a big muscly dude, so I think he was probably taking steroids, but none of my business. All right, whoops. But I always think of that sweaty guy in my mammalogy lab when I think of an overactive thyroid. Because our thyroid hormone promotes metabolism, it's also going to work in conglomeration with growth hormone for growth and development. And because this is also fueling growth and development, this is hugely important for nervous system development. Infants and children have high concentrations of thyroid hormone. They need high concentrations of thyroid hormone because their bodies are growing very, very quickly. And if their brain and their spinal cord and their nerves can't keep up with the growth of their muscles and their bones and everything else in their body, that's not a good combination, right? Their nervous system has to be able to keep up with the rest of their body in terms of growth and development. So thyroid hormone plays a huge role there. So some ingredients in thyroid hormone, something called thyroglobulin. That's the major protein that's involved in our thyroid hormone. And then, of course, the iodide ions. This is one, has anyone ever watched those like prepper shows? Like where they kind of prepare for like the end of the world or Armageddon or whatever, and they have all these like underground bunkers and they store things. One of the things that they like to store is iodide tablets. I may or may not be an amateur prepper, just saying. So iodine tablets, the reason people keep them is because in nuclear explosions, one of the common radioactive elements that goes into the air, which we're very close to radioactive, meltdown up at Beach Bottom. One of the major radioactive elements is iodine, and radioactive iodine comes into your body, and because your follicles crave iodine so much, they just suck it all up, right? And so imagine if you're sucking up all of this radioactive iodide, right, into your body because of a nuclear explosion. Now you don't have thyroid hormone, or your thyroid hormone that's floating around all of your body is now radioactive. Uh-oh, right? That's dangerous. So in the case of nuclear meltdowns in the end of the world, so to speak, a lot of preppers keep iodine tablets on hand to give their body enough iodine so that they don't soak up the radioactive iodine that's in the environment. And that's one of the reasons, because it's your body really soaks it in. We also have our salt, for example. If you look at the label on the salt, like the Morton salt with the girl with the little yellow umbrella, like it says iodized salt on it. There's iodine added to our salt to help us get our daily dose of iodine. Other countries don't have that. You go to South America or Africa or even parts of Europe, their salt doesn't have that. And if you look at their diets, they eat a lot of fish and vegetables. They don't need to have iodized salt because they're getting the iodine through other ways. Anyways, this is just showing you how it comes in. It's in your blood, and then it's absorbed through your follicular cells and used to make T3 and T4. Hyperthyroidism is when you have too much thyroid activity, right? So an example of this would be, again, we talked about how that thyroid kind of expands a little bit, produces a goiter in those cases. Graves' disease is the most common example of hyperthyroidism. This is where your immune system produces those abnormal cells, and the abnormal cells kind of act like thyroid cells in your body. So you would think people that have a hyperactive thyroid, because thyroid is your fire, thyroid is your metabolism, they would be super skinny and full of energy. But in the case of Graves' disease, they're kind of the opposite, right? They have a high body temperature, so they're that kind of sweaty guy, right? But they're not very thin, and they have lots of issues with their body because their immune system is pretending to be thyroid hormone, right? And so instead of the thyroid hormone going to all of the target tissues like your muscle tissue and your nervous tissue, it's these immune cells that are there not doing anything, kind of blocking, right? And so that's called Graves' disease. Hypothyroidism is the opposite. So this is where you have an underactive thyroid. So weight gain, cold intolerance, you're cold all the time, very slow heart rate, thin hair, brittle nails, all of that, right? This is also going to repress your immune system and strongly affect your cognitive functioning. You might actually have like a foggy brain. You might not be able to think of words or remember things as well because that metabolism is slower. Congenital hypothyroidism. So this is when the infant's born, right? The thyroid is just not functioning properly. And without a properly functioning thyroid, you're going to have serious physical, mental delays in development. Oops. So let's talk about calcium homeostasis. Of course, we mentioned calcitonin and the parathyroid hormone secreting, or the parathyroid gland secreting parathyroid hormone. We drew this way back in the day when we were talking about bones, but let's do it again because it's super important to understand, right? Calcitonin and PTH are our key players here. Oops, I'm gonna use this one. Calcium homeostasis. Let's say blood calcium levels drop. Maybe it's been a while since you've ate some dairy products or put calcium in your body because you are on a crazy diet or whatever, right? So your blood calcium levels drop. In response to that, your parathyroid gland is going to release parathyroid hormone, PTH. What PTH does, PTH is going to work on your kidneys. At your kidneys, it's going to increase calcium reabsorption. In other words, it's going to say, hey, you know that calcium we were just about to pee out? Can I have that back? I'm not ready to pee that out yet. Right? In your intestines, it's going to increase calcium absorption from your food. Nope, we're not going to poop that out. We're going to put it back into our body. And in our bones, it's going to activate, what's the name of the bone cell that's going to dissolve bone matrix? Osteoclast. Yeah, I love it. Osteoclast. It's going to activate osteoclast. All of this increases blood calcium levels. Uh-oh, now we have too much. Isn't that the thing, right? It's nonstop teetering and tottering. It's always back and forth. You're never at a complete standstill with any homeostatic mechanism. It's always hemming and hawing. So now we have too much blood calcium. So what's going to be released here? Calcitonin. Right? Calcitonin is released from your thyroid gland. And it's literally going to do the exact same thing in reverse. So calcitonin is going to affect your kidneys. It's going to increase secretion. You know what? Remember all that calcium I said I wanted? Just kidding. You can pee it out. I don't want it anymore. In your intestines, it's going to decrease absorption. Nope. I know that you just ate a whole bunch of yogurt, but I don't want it. I don't want that calcium. I don't know what happened here. Sorry. There we go. And then our bones, it's not the osteoclasts that are going to be activated, it's the osteoblasts. our osteoblasts get activated. Guess what all of that does? Drops our blood calcium levels, right? It's this non-stop, but calcitonin and PTH are key players, keeping blood calcium at constant levels. And as we've seen, we need calcium in our bones, right, for mineralization so they can get hard. We also need calcium in our skeletal muscles, right, for that sarcomere contraction, right? It's going to bind to the tropomyosin and allow our myosin heads to bind. We also need calcium at our motor end plates and at the axon terminals of all of our neurons, because calcium coming in is going to kick the neurotransmitter out, right, at that presynaptic cell. So we have to have enough calcium to do that. So PTH is going to increase the release of calcium ions from our bones, increase the absorption from our intestine. Right, act on our kidneys, bringing it in. Okay, this is showing you exact same thing that we just drew over there. And this is the exact picture with a lot more visualization than the words that I drew, but it's the same general idea, right? Blood calcium levels decrease. We have some types of receptors in our blood that are detecting that. That's going to cause our parathyroid hormone, or parathyroid gland to secrete parathyroid hormone. And calcitonin does the opposite. Calcitonin is going to be released to decrease blood calcium levels, get our osteoblasts back and working properly. Okay, our adrenal glands. I've been taking, oh, you know, I was looking for my phone, but my phone's over there. Oh well. I've been taking pictures of a lot of my drawings because some students have been messaging me about them, and oh well. If you do take any pictures of these, I would like them. You can message me them and remind if you want. Let's talk about adrenal glands, right? So adrenal glands, moving into our next little endocrine gland here. Adrenal glands have a different organization than some of our other one, than like our thyroid, which is pretty straightforward. Remember, our adrenal glands, adrenal glands are like little hats that sit on top of our kidney. So here's our kidney. The adrenal gland is like this, right on top of the kidney. And it has three major areas. It has something called a capsule. The capsule is kind of like the skin of the apple. It's just the outer casing. Then we have this cortex. The cortex is the endocrine part of our adrenal gland. So this has the endocrine function. It's going to secrete hormones. Whereas this medulla, which is the inner part, this is neuroendocrine. And so it secretes hormones that act like neurotransmitters. Yeah. Secretes hormones that act like neurotransmitters. So sometimes we call them neurohormones, kind of like a mashup between the two words. So our cortex produces steroid hormones. The adrenal cortex has three major zones. And you'll get to know these very well tomorrow at 9. This is all part of our histology. It has something called the zona glomerulosa, which sounds like a Harry Potter spell to me. And then the zona fasciculata, and then the zona reticularis. So the zona glomerulosa, this is densely packed. This is the outermost area. So the zona glomerulosa is this piece here. We're talking cortex. So this is the area just beneath the capsule. ZG, right? These are mineral corticoids that are going to be released there. Mineral corticoids are going to stimulate the absorption of minerals. You might be able to think of a couple of important minerals that we've talked about so far this semester. One that rhymes with schmodium, right, sodium. So a mineral corticoid that's going to be released here from the zona glomerulosa is going to stimulate the absorption or secretion of sodium. We'll look at that one. Our zona fasciculata, the next little piece, this is going to secrete something called glucocorticoids. Glucocorticoids. These are, and actually our reticularis does the same thing, glucocorticoids. And androgens. Androgens are sex hormones. Sex hormones like testosterone and estrogen.
So they secrete those? Or
Mm-hmm. So we're used to thinking about just the testes and ovaries secreting estrogen and testosterone, but this part of your adrenal gland secretes small levels, which is why even at young ages, children who don't have active reproductive systems yet, like my kids, 7 and 8 years old, they still have male-like and female-like characteristics because of the low levels of testosterone and estrogen in their bodies. My son kind of looks like a boy, right? He's got broader shoulders, he's a little bonier, right? My daughter is a little softer. I don't want to use the word curvy, that's not a good way to describe a 7-year-old, but she's softer and she has rounder features, right? Whereas my son's more kind of pointy. And that's because of the influence of testosterone and estrogen on their tissues. Testosterone and estrogen are also needed for other things other than reproduction. So we need them for development, skin, bone development, muscle development, things like that. And so that's where they come from, on this part of the adrenal glands. And glucocorticoids, we didn't mention these. Glucocorticoids, these are your quote-unquote stress hormones. These are your stress hormones. So these are the hormones that you probably have a lot of throughout this semester, especially around exam time or going into the lab tomorrow. We got so much to learn or whatever. Right, so this is showing you the exact same thing. And you do have to know these different regions for your lab practical. And the way it would be asked, and I'll review all of this tomorrow, the way it would be asked is I would say to you, this is the adrenal cortex. Which layer is this? So I'd kind of lead you into it. So then you just have to be able to identify glomerulosa, fasciculata, reticularis, just the 3 zones right on top of each other, which we're not getting into the histology tonight. We'll look at it more tomorrow, but they're just labeled right on top of each other. Let me grab other colors and I'll just kind of illustrate it over here. So you have glomerulosa, fasciculata is next. This is why bringing multiple colors is helpful. And then reticularis is right on top of the medulla. All right. So one of those main mineral corticoids is aldosterone. So when we were talking about mineral corticoids, our major one, the most, I would dare to say the most important, is aldosterone. This is going to increase sodium in the blood. So it's going to do this by, it works in a couple of ways. So there's a couple of ways our body gets rid of sodium, right? Namely, we pee it out if we have too much of it. Sodium is a water-soluble mineral, so if we have too much of it, we just pee it out. If we don't have enough, we retain it, we reabsorb it, right? So it's going to mainly work on the kidneys, right? Which is nice because look at where the adrenal glands are. They're right on top of the kidneys. So, and by doing this, by regulating sodium levels, by default, our body is also regulating water because water follows salt. Water follows salt. Where there is salt, water will soon follow in our body, in living systems. Think about this, all you Marylanders that like to eat crabs and covered in Old Bay, right? You eat some crabs, and an hour or so later, or as you're finishing your 7th or 8th crab, maybe your rings are a little tight on you, or maybe your lips are puffy. It's because of all the sodium that has touched those areas has drawn water to those parts. And so water follows salt. And so if your body's retaining sodium, it is therefore retaining water. So we'll look at how that works. Aldosterone works to maintain blood pressure. By maintaining sodium and therefore water levels, we maintain blood volume. And if we maintain blood volume, we maintain blood pressure. So aldosterone is key in regulating blood pressure. Now, us Americans with our high sodium diets tend to think of having high blood pressure as a bad thing, right? We're like, well, most of us have high blood pressure, so why would we want to keep our blood pressure high? Why would we want to have aldosterone? Well, because 100 years ago, before McDonald's and before all of this pre-packaged foods that had too much sodium in them, we didn't have a blood pressure problem. And so we needed to retain water in order to retain our blood pressure. And so our Americanized diets have kind of tainted the way we think about blood pressure in terms of survival, but it really is an important mechanism. So aldosterone works by working with something called the renin-angiotensin-aldosterone system. So I'm going to erase this because I don't want it, or I take it away. The renin-angiotensin-aldosterone system. It's going to work like this. Remember our kidneys, which filter our blood. They have a high kind of penetration level in our blood. If you think about I'm really hungry, so I keep thinking about food. Think about like making like hamburgers from scratch, and you have the ground beef and all the spices and the celery and onions, and you can't mix it with a spoon, right? It doesn't turn out right. You have to actually get your hands in there and mix it. That's how your kidneys are with your blood. They're literally like elbows deep in your blood, like sorting it out, right? Shifting it around. And so your kidneys are your major regulator of everything in your blood. Remember, we talked about kidneys when we talked about calcium homeostasis, right? They're going to either eliminate the calcium or reabsorb the calcium. And so your kidneys are always detecting blood levels. Your kidneys detect low blood pressure, right? Low blood pressure can be caused by two things. It can either be caused by not enough blood cells or not enough blood volume. And so your kidneys release something, a hormone, because we're talking hormones. Your kidneys secrete renin. R-E-N-I-N. Renin goes to the liver, and the liver converts renin to something called angiotensin 1. And angiotensin 1 goes into the blood, and in the lungs, angiotensin 1 is converted to angiotensin 2 by an enzyme called angiotensin converting enzyme. Isn't that nicely named? Angiotensin 2 goes to the adrenal glands and causes the release of aldosterone. When aldosterone's released, it's going to trigger your body to reabsorb lots and lots of sodium. Imagine that this is your blood. And what we've just done is told your blood that it needs to absorb more sodium. Your body at this point is freaking out because there's so much sodium in your blood. It's super concentrated. But there's a hormone that can be released that tells your body to reabsorb water. What is it? Antidiuretic hormone, right? And so your blood, which is super concentrated now because of aldosterone, is going to become more dilute because aldosterone triggers the release of ADH. And ADH is released from the posterior pituitary, right? And so this blood that's super concentrated now becomes much more dilute. Remember, water follows salt. How does that happen? Well, in this system, it happens because ADH and aldosterone are BFFs. Where there's ADH, there's aldosterone. Where there's aldosterone, there's ADH. They go hand in hand. They're always together. Aldosterone is also going to work to maintain acid-base balance. So not only is aldosterone going to regulate blood pressure, but it regulates acid-base. I'll give you a little look, a peek into AMP2. Sodium and potassium always move opposite of each other, right? They always move opposite of each other. Well, just like aldosterone and ADH are BFFs and they're always together, potassium and hydrogen ions are always BFFs and they're always together. So wherever you have sodium, you don't have potassium, and therefore you don't have hydrogen ions. And hydrogen ions are acid, right? Hydrogen ions are acidity, they're low pH. And so if you have lots of aldosterone, then you're going to have a higher pH. If your pH starts to drop, 736, 735, oh no, we're too acidic, guess what your body's going to do? Your body's going to start to reabsorb potassium. Your body's going to start to secrete sodium. So, because where there's potassium, there's hydrogen. Where there's potassium, there's not sodium. Sodium and potassium are always opposite of each other. So acid-base balance, because sodium, potassium are opposites. All right, so major factors that increase aldosterone release are having elevated potassium levels, right? That gets back to our acid-base balance. Having a decrease in blood pH, because where there's potassium, there's also hydrogen, and that angiotensin II hormone that we drew here, right? That's going to trigger aldosterone to be released. Glucocorticoids, these are those stress hormones like cortisol, right? This is that nervous, anxious feeling. Cortisol puts you in this kind of constant fight or flight state where your body is conserving energy and prepping for a major sprint to out of the dark alley or whatever. So cortisol is going to help you respond in times of stress. Of course, in our lives, we're exposed to stress pretty much non-stop. So this leads us to a deeper understanding of the stress response. Cortisol receptors are all over our body, right? In the liver, when cortisol is present in the liver, it's going to stimulate something called gluconeogenesis, which is basically the production of new glucose molecules. Your body's saying, oh gosh, we're so stressed, we need to have lots of glucose available because we need to fight or flight, we need to run, we need to have lots of glucose available so we can make all this ATP and we can do all the things that we need to do in this high stress environment. It's going to increase blood glucose levels. So glucose floods into the blood. Glucose increases in your blood. It's almost like eating lots of sugary foods, like eating a pixie stick, right? Or drinking a soda, right? stress hormones have the same effect on your blood as eating cookies because you're putting that sugar directly into your blood, putting that glucose directly into your blood. So this is also going to induce the breakdown of proteins in our skeletal muscle. Your body's saying, oh my gosh, we're stressed. We need to have all this ATP energy available. We need to make sure that we can fight or flight, right? We're in survival mode. That's what cortisol means in your body. Cortisol in your blood means survival mode, right? And so those proteins that are in your muscles are going to be broken down. This is why people that are constantly stressed, not only do they have trouble losing weight because they have this high glucose level in their blood, right, which is going to mess up their insulin and all of that stuff, but it's also going to make it really difficult for them to do things physically. It's also going to act on your adipose tissue to release fatty acids, right? It's going to convert them into glucose in the liver, which that sounds like a good thing, going back to the weight loss thing, but putting all of that glucose in your blood can mess things up in the long run. Not only all of that, but it's also going to decrease your white blood cell activation. It's literally suppressing your nervous system, which is why generally about this time of the semester, I see students that are starting to get sick. It's also because we're all in lab touching all the same models and not everyone washes their hands. But it's going to strongly affect your immune system. I can tell you this, I usually don't get sick through the semester, but as soon as the semester's over, I get sick. It happens to me all the time. Because it's kind of like, right, all that work's over, and now, all the infections come in. Decreasing all of those white blood cells in your body can lead to lots of sicknesses because it acts as an anti-inflammatory agent in your body. When you're under stress, your body's natural inflammatory response isn't working like it should. So those adrenergic steroids, right? These are things like testosterone and estrogens that are released in that reticularis area. And so small amounts, but same general effects as the testosterone and estrogen from the gonads. In the adrenal medulla, we have that adrenal medulla drawn over here. It's the very center of our adrenal glands. This is where those neurohormones are released. So these neurohormones, these are things that are activated by our sympathetic nervous system. So these are things like epinephrine. We talked about epinephrine before. Epinephrine is a neurotransmitter, but epinephrine can also act as a hormone when it's released from your adrenal glands. Epinephrine goes by the name adrenaline, right? When you get that system-wide fight or flight response, when you feel that nervous anxiousness all over your body, it's because your adrenal medulla is releasing epinephrine. Your adrenal medulla is releasing these neurohormones that are affecting all of your tissues, right? It's a coordinated, integrated response when your adrenal medulla releases epinephrine. So, moving on to our pancreas. Our pancreas, I'm going to erase adrenal cortex. Our pancreas has a couple regions, and our pancreas has two main functions, right? Our pancreas is actually a digestive organ with an endocrine function. So it has pancreatic islet cells and then the pancreatic acinar cells. Our pancreatic islet cells, these are the endocrine cells. These are the ones that are releasing insulin and glucagon. I'm going to draw it like this. The acinar cells have a digestive function. Right, so these are secreting enzymes and buffers and things like that into the small intestine. So our pancreatic cells secrete, our alpha cells, I should say, secrete glucagon. Our beta cells secrete insulin. I remember that. This is a weird Jamieism. Alpha, I know there's an A in beta, but just pretend there's not. Alpha starts with an A, and glucagon has an A in it. So I remember that. And then somatostatin, remember that one? That was kind of turning off growth hormone. So that's released by the delta cells. There's our pancreas, looks like a little fish. You'll see the histology of this in lab. Glucagon, so glucagon's going to be antagonistic to insulin. So this system is going to work similar to our calcitonin and PTH, where we have a decrease in blood glucose levels, and so we need to increase them by releasing glucagon. Glucagon's going to increase our blood glucose levels. Insulin does the opposite. And the way this happens is not so much by regulating kidneys and absorption and all of that stuff like we saw with calcitonin and PTH. This is strictly telling our cells to either let glucose in or to push glucose out. That's all it does. These hormones work specifically on the cells themselves. So the breakdown of glycogen is called glycogenolysis. So glucagon is going to promote glycogenolysis. Glycogen is stored glucose, and when glucagon is available, your cells are basically saying, we don't have enough glucose, we need more, so let's go ahead and take this big old bucket of glucose we have over here, we call glycogen, and let's start taking this glucose out and putting it into the blood. Right? Glycogen is stored form of glucose. So by releasing glucagon, you're releasing the glucose stores. Right? Glucose is actually stored in the form of glycogen in our skeletal muscle cells and in our liver cells, the two major metabolic places in our body. Glucagon is also going to bring about the process called gluconeogenesis, which is taking things like proteins and fats and turning them into glucose. So if you don't have enough glycogen or you don't have any sugar floating around in your body's going to use fat first, and then it will use protein to make glucose. So glucagon can also be used to break down protein. As we mentioned, if you don't have fatty acids available, your body prefers glucose first because it's easiest, and then fatty acids. And then if there's not enough fat available, then it will start breaking down protein. And that can be dangerous. You'll talk about that more in AP2 when you do nutrition and metabolism. It can create a state of acidosis in the body. Those ketone bodies are formed from the breakdown of fatty acid molecules. It's basically an accumulation of pyruvate, which is a byproduct of glycolysis, and it can drastically lower your blood pH, which again, we know our blood pH has to stay in that 735, 745 range, so if you don't have enough of it, it could be dangerous. So glucagon release is triggered by a decrease in blood. It's also triggered by sympathetic stimulation. So you're nervous, you're anxious, you have that fight or flight thing going on, glucagon is going to be released. Why? Because you need to fill your blood full of glucose so that you can fight or flight. Right? Your metabolic reserves are activated in that case. Also, those catecholamines, the adrenaline, the epinephrine coming from the adrenal medulla, that's going to stimulate glucagon as well. Lots of proteins, bringing lots of proteins into your body will also do that, because your body, if you're bringing in protein, high levels of protein, you need to bring in glucose or have glucose available for metabolic purposes, because your body doesn't want to break down protein for energy. Oops. Oh, it's starting to freak out. Here we go. I'm just going to do it like this. Okay, insulin. Insulin, this is our major satiety type hormone. So this hormone is going to be released when you're eating and after you're eating. So you feel full generally when insulin starts to be released. You eat food, your digestive system breaks it down, it starts to be absorbed into your blood, and as your blood glucose levels rise, insulin is released. And insulin will pull the glucose into your cells. And as that's happening, simultaneously, your brain's saying, you're full, you've had enough, we're good. Right? Which is why if you eat fast, you're missing that signal and probably overeating, right? It's promoting the uptake and storage of nutrients, right? It's going to synthesize glycogen in the liver, whereas glucagon did the opposite. So this is literally the opposite. I hate this computer. This is literally the opposite of what we had going on with glucagon. So we can draw the same basic feedback, that same feedback loop that we had when we did calcium. High levels of blood glucose, insulin released, cells uptake the glucose into them, blood glucose levels drop, glucagon's released, and so on and so forth. The big difference here, kind of behind the scenes, you also have all of that glyconeogenesis, glycolysis, things like that that are happening behind the scenes. So let's go on to a couple other smaller glands in the body. We've hit all the major ones. The pineal gland on the back of the brain, we looked at it in lab, it's kind of behind the thalamus. It secretes something called melatonin. Melatonin is another neurohormone, so it acts like a hormone and a neurotransmitter. It kind of works as both. This is going to help regulate our light and dark cycles. In this room, obviously, we have all of the synthetic light, I couldn't say it, synthetic light. So we're in here and we're nice and awake. But I bet if we turned off the lights and we didn't play on our cell phones, we would all slowly drift off to sleep because melatonin levels rise when the sun goes down. And so that melatonin is going to kind of turn off your body, turn off that, remember that reticular activating system that kind of kept you alert and awake? Melatonin shuts it down for the day and allows your body to restore and re-energize. The thymus is another gland of our endocrine system. So the thymus is our endocrine gland in the mediastinum or mediastinum. It kind of drapes over your heart. It's present and very large when you're born, but by about the age of 20, it's almost totally gone. It's very active as you're growing and developing, but once your immune system's fully developed at about around 18, it has no purpose. The whole purpose of the thymus is to build up your immune system and make you into a super healthy adult. And so as you're growing and you're a child and an adolescent and you're being exposed to all these different antigens and all of these different viruses and bacteria, your body's basically stockpiling a memory of all of the things you've ever been exposed to so that when you're an adult, hopefully, you don't get sick as much, and it's because of your thymus. So thymosin and thymopoietin are these hormones that kind of drive the growth and production of white blood cells at that stage. So the sex hormones, we've mentioned these briefly already, the testes and ovaries, right, responsible for producing sperm and eggs. They produce the steroid hormones, estrogen and testosterone. The testes produce testosterone. Testosterone is important not only for bringing about sperm development, but testosterone is also important for secondary sex characteristics, as well as increased calcium deposition on the bones, increased muscle mass, things like that. Elevated testosterone levels is also going to increase growth hormone levels, right? Growth hormone is our metabolic hormone. So having lots of testosterone is also going to fuel your metabolism. Testosterone, high testosterone levels actually inhibits GnRH. So if you remember, we had like a cascade pathway drawn over here where we had GnRH stimulating FSH or LH, and then down here it was stimulating the release of testosterone. Well, once testosterone's been released, it inhibits GnRH. It's actually a feedback loop that says, okay, we got enough testosterone down here, we don't need any more, and GnRH turns off, and then turns back on a little bit later and makes some more, right? So it's a negative feedback loop is what it's called. Testosterone is a hydrophobic hormone, right, which means it's transported by a protein. It has anabolic effects, which means it builds structures like muscles and bones and hair growth and things like that, right? All the things that we associate with maleness, right? Estrogen and progesterone are secreted by the female ovary. Males have a small amount of estrogen from their adrenal glands, just like females have a small amount of testosterone. Estrogen is produced in response to the LH and FSH, just like we had testosterone being produced in males. And estrogen has that similar effect, right? It's going to produce secondary sex characteristics in females, breast development, menstrual cycle, etc. Progesterone is going to bring about ovulation and help maintain pregnancy. So progesterone is a purely kind of fertile pregnancy type hormone. Estrogen is needed for your daily life and daily activities. You need estrogen for cholesterol and things like that in your body. Even males, right, need it. But males don't really have progesterone. Progesterone is purely about releasing an egg and maintaining a pregnancy. That's what it's there. Progesterone is responsible for anyone's ever been pregnant before, or know anyone. Progesterone is the kind of icky, sick hormone. It makes you feel yucky in your first trimester of pregnancy, or if you've ever been on birth control, those progesterone pills they just make you feel so gross. Everything smells bad and tastes bad, and it's awful. Your fat tissue also releases hormones. So we've moved from strictly endocrine-based glands that have an endocrine function, and we're talking about other things that have a primary function, but they also have an endocrine function. So like our gonads, for example, our adipose tissue, our fat tissue releases a hormone called leptin. Leptin is going to be released kind of like in conjunction with insulin. When insulin's released, your brain says, we're full. Well, at the same time, leptin is being released, delivering that same signal. Leptin's released when your fat stores become activated, when you start to kind of pile away some extra calories, pile away some extra triglycerides. Your body says, yep, we've had enough, we're full, right? So it's closely related to the amount of adipose tissue you have. So in other words, the more fat tissue you have on your body, the more leptin you produce. Our heart has an endocrine function also. Our heart releases something called ANP. ANP does the opposite of aldosterone and angiotensin. Remember angiotensin and aldosterone, right? Increasing blood pressure. ANP decreases blood pressure. What happens is all of a sudden your heart feels this huge increase of pressure, this huge return of blood, and your heart says, whoa, we need to calm it down. And ANP is released, and it slows everything down. It dilates the vessels. It allows your body to kind of restore a lower blood pressure naturally. So it's going to vasodilate and allow all of your major arteries to kind of relax there. ANP works to secrete the sodium ions at the kidneys. And if you secrete the sodium ions, you're also going to secrete the water, because water follows salt. You'll decrease your blood volume and decrease your blood pressure. And we did this already, the EPO, I left EPO off, I'll add EPO. But this is all that renin-angiotensin system. We talked about fluid concentrations with that, plasma concentrations. We know that. Let me just add EPO to this, because your kidneys detect renin, renin goes to your liver, but renin also stimulates EPO. EPO stimulates red blood cell production. That was the one thing I did not include. So with that, we wrapped up this chapter. We should be able to finish special senses. We have 3 lectures left. We should be able to do that. Hopefully.